Today I'm going to be talking about topological quantum computing. Just in general, I know I made you read that paper, and that'll be a part of it, but I want to talk more both about the paper and more generally about the subject. And so topological quantum computation is, to understand that, we first have to understand what topology is. So topology is a branch of mathematics, and the way to define it that pisses off mathematicians the most is that it's the way study of properties that are resistant to local deformations. So I could make a lot of jokes about topologists, but I've limited myself to just three. On the left is the classic donuts and coffee cups are the same, because you can continuously deform one into the other. And what topology kind of measures is that, like some properties, like the fact that there's a hole in the middle, like the donut has a hole and the mug has a hole in the handle, that stays constant under this kind of deformation. And so this is basically what topologists study is just donuts and coffee cups. In the middle, it's a fitting shirt for Valentine's Day, because this is why you don't date a topologist, because they send you some mixed signals. And on the right is what topologists do instead of like watching sports or having fun. They just look at everything in terms of donuts. But that's useful. It's useful that they're doing all of that. Because quantum computers, the big problem with quantum computation, obviously, is that it's very sensitive to basically everything. There's a lot of sources of noise in the environment. And so if we can build a quantum computer that is resistant to deformation, then we'd have the most stable qubits imaginable. And so to actually get to how we're going to build that kind of quantum computer, we are going to need to take a little bit of an Odyssey, as I called it in the title slide. So we'll be covering kind of all these topics until at the end we'll touch on quantum computation. So first, we need to, before we get into all the stuff about anyons, we need to describe what are particles in the first place. And quantum field theory, what quantum field theory tells us is that particles are just excitations in a field. You have some field, you apply a creation operator to it, and you get a particle. You apply a creation operator to the electromagnetic field, you get a quantum of the electromagnetic field, which is a photon. Apply a creation operator to the electron field, you get a quantum of the electron field. And in general, you can determine the mass of this particle because E equals mc squared. It's just going to be this energy gap you get when you have the particle there versus when you don't have the particle there. But this framework is a lot more general than your kind of standard particle physics here, like what we generally like to think of as like the vacuum or like empty space, where you have these like well-defined fields. We can also define these things called quasiparticles, which happen just in any system where you have you're able to have these localized excitations that you can create and annihilate. And so one example that's might be a bit more familiar to you than what we're going to get into is if you have some kind of solid and you have some vibrational modes in that solid. So this can be treated because if solids are actually, to first order, they're just a bunch of quantum harmonic oscillators. You can apply creation and annihilation operators to those, and you get these quantized sound waves, which we call photons. And so in the same way photons are quantized light waves, you get quantized sound waves. And these are examples of quasiparticles that appear in certain condensed matter systems. So let's try and build our own system that has quasiparticles. So I'm going to introduce to you all a code called the toric code. So we have, the way this is going to be set up is we have a bunch of qubits on the edges of the lattice. The edges is very important. They're not on the vertices, on the edges of the lattice. And we describe them as kind of living on this, you can think of it as a plane, but we loop the ends back around each other. So if you have, I'm going to steal this for an example. If you have this plane and you identify the edges, you get a cylinder. And then if you identify those edges, it wraps back around itself and forms a donut or a torus. So that's why this is called the toric code. On this toric code, if we have a bunch of these qubits in certain states, we can move between them using these plaquette operators. And so this is we imagine if you fill these all with sigma z eigenstates, so spin up and down in the z direction, then the left one is just going to be some kind of eigenvalue operator for vector. And the second one lets you move between these kinds of loops by applying sigma x to all of the edges around this square. And so these are like kind of operators you can define on this lattice of qubits. So we can define, so what I've just described to you is not really a quantum system because we haven't defined the Hamiltonian yet. So we can define the Hamiltonian like this. We take this product over all of the A's and all of the B's. And I'm going to give a derivation of the ground state that probably doesn't hold up to mathematical scrutiny, but it is correct in the sense that the end result is what you'd expect. So, oh, by the way, if I'm going too fast, please, I don't want this to be like a huge talk. I want, if you have questions, I want this to be more of a discussion. If you have anything that like, oh, I'm going too fast, or yeah. So feel free to speak up if none of this is making sense. So we can derive the ground state as kind of as follows, where any set of closed loops is going to be a ground state of these AS operators. And the way you can see that is that each of these AS, it's going to be, if you have a set of sigma z eigenstates, it's going to be basically it's the product of all of the spins. So because it's going to be plus or minus 1, if there is an even amount of plus 1 or minus 1, then it's going to be 1. And if it's there's an odd number, then it's going to be negative 1. So you see around this vertex, we have two of one state and two of the other, so that's going to be a product of 1. But if we had, like this, if this was like a blue edge, whatever, this could be spin up or down, then we're going to have, it's going to be raise the energy of this vertex. And so that's why any set of closed loops, because it has no kind of open ends, that's going to be kind of the low, because we have the negative side, that's going to be a low energy state of the system. But we, as I mentioned in the previous slide, we can move between these sets of closed loops using these B operators. So our ground state must end up being indifferent to all of the B's. And the only way that can happen is if it's this massive superposition of all of these possible closed loops that are reachable by these big B's. So that you kind of get this very massive entangled ground state. But I mean, how massive really is it depends on what loops are going to be reachable by these B operators. So this is a kind of an interesting topological question, because in the plane, you can take any closed loop and you can deform it. You can use these B operators to deform it into any other closed loop. But in the torus, you get these 4 loops that all can't be transformed into each other. And I wish I had like some kind of donut here that I can actually draw out these 4 loops. But imagine this one can be contracted all the way to just the point, where you have this, so it basically doesn't go around any part of the donut. So, but if you imagine like this one goes around the kind of small circumference of the donut. So there's going to be no way to, using these small local, because the BPs all act locally, there's no way to go from that one where it's not wrapped around to the one where it is wrapped around. And so there's no way to get from here to here. And likewise there's a loop going around the long way of the donut. And then there's the sum of these, both of these, where it's going both around the long way and around the short way. And so what you can end up doing, and this is kind of tangential to what I'm going to be talking about today, is that you can use these cleanly separated ground states as your qubits to build up an error correction scheme. And then this fantastic paper by Wong that you all should read on how to do exactly that. But this is exactly what I'm going to be talking about today, because even though it is topological and it is quantum computing, it's not topological quantum computing. We'll see what it is. This is called topological error correction if you're genuinely interested in this. So now that we have our ground state, we have these. Our ground state can be either of these 4 distinct massive superpositions. We can talk about how you move between them, and we move between them using these string operators, where you basically just kind of create excitations. You'll see if we apply this the string operator to this line, like this. If you apply the A operator here, like this one is happy, this one is happy because they're even. But this one is not happy because it has an odd number of spin down state. So it's going to have this one's going to get a negative sign, and the one here is also going to get a negative sign. So we get these local energy excitations in this like localized to the ends of this string, and we can move these excitations around using these sigma x's. And so you might these look a lot like kind of particles, but as it turns out, and this is like a big twist that I've been building up to, these are not the only kind of excitations, because there's this big emphasis on duality in the toric code, where if you go all the way back to where I defined this Hamiltonian, there's really not a big difference between the A's and the B's. They're defined very similarly. So what we can do is instead, I've kind of been focusing on the A's as determining this energy and the B moving stuff around. But we can equally define the B's as being some kind of energy measure and the A's moving stuff around if we go and look at the dual lattice, where the dual lattice is the lattice of faces, and it has the same edges, but the roles of the faces and the vertices are flipped. And so we can create energy excitations in this dual lattice using sigma z operators. And these are called magnetic vortices for some reason. I don't know why. The other ones are called electric charges. I also don't know why. They're not electric charges. They're completely neutral. And so in this way, we have these two quasiparticles that can be created in this toric code. Any questions on, because that's a lot of information. Anyone have any questions about what I've discussed so far? Yes.
Is there some sort of analogy going on with the A and B operators?
Yes, so this duality is very deep in the toric code. Again, I'd like to refer you to this excellent paper by Wong, where this duality is really explored, and it's there's links to homology and cohomology in these in this kind of duality between your primary lattice and the dual lattice.
Could you repeat the definition of the dual lattice?
So in the dual lattice, you're going to, so the edges remain the same, but you flip the roles of faces and vertices. So on each of these faces, we're going to draw a vertex, and we're going to, you'll see that each of these faces is basically just, it's about the vertices that aren't there, basically. It's like, music's about the notes you're not playing. So you just fill in all these gaps, and that forms its own kind of lattice. Okay, so we're gonna come back to the toric code, but now I have to talk about particle statistics. So we can define, so now that we have these two quasiparticles, E and M, we can define the statistics of these quasiparticles, which is just the phase change they acquire by the exchange of the particles. So if you take your two particles, and I'm talking literally move them around each other, they're going to acquire some kind of phase. And if you do that with a particle with itself, then you get the exchange statistics of the particle. And so what the paper I made you all read for today talked about was a method to compute the statistics of these quasiparticles just by kind of looking at the model and operators within the model. So let's kind of run through, before we run through,
Actually, what is the intuition that you would say when you think about statistics? Because if you just simply think about them as exchanging their locations, wouldn't the path of the exchange be?
Yes, so interesting point to bring up. In that, so there is a kind of intuition you can. This seems like the way you're going to exchange the particles will matter in the method of exchange. It actually ends up not mattering for some reason. For some reasons I'll get into. I don't have a good intuition. I'm not gonna. There is some intuition if you know a lot of quantum mechanics already, where you can build up these kind of magnetic flux tubes and braid them around each other. That ends up being completely independent of. You can see that it becomes path independent. But for now, we're just going to assume we have these statistics that are path independent, and we'll see what the consequences of this are. Because this is not a weird condensed matter thing, because real particles have statistics too. And so all kind of real particles, like non-quasi-particles, fall into one of these two categories. They're either a boson or a fermion. Who here has not heard these terms before? Okay, then just for you, if a boson is one where the phase change is like +1, and a fermion is one where the phase change is -1. And as a consequence of the spin statistics theorem, this very deep result in quantum field theory. I don't know how much particle physics I'm allowed to do here. I thought we hated this, guys. But for now, I'm just going to be talking about the spin statistics theorem, where every real particle in 3D, like 3 + 1 dimensional space, is either a boson or a fermion. And this statistics is determined entirely by the spin of the particle. And so we just need these three things, where they're either a boson or a fermion, these are determined entirely by the particle. And the fusion, which I'll get into, of bosons and fermions is also entirely. So the idea is that we can fuse real particles together. So we know that, perhaps, well, I'll go backwards. So if we bring two bosons together, then they stay a boson. Like that makes sense, right? Like if you bring something around, then if something is unchanged by this exchange, then two of them is also going to be unchanged by this exchange. The more interestingly, the fusion of two fermions is itself a boson. So we get these things called Cooper pairs in superconductors, where you basically have two electrons. What it is basically two electrons. I don't know how to do it. They team up to form this boson. And that's interesting because normal electrons have to abide by the Pauli exclusion principle. But these pairs of electrons, because they're bosons, they don't. So they can flow with zero resistance. And that's how superconductors work, is you get these fusion of fermions into a boson. And the same thing happens with like helium nuclei and superfluidity, where all the constituent protons, neutrons, electrons are all fermions, but you get bosons out of them by the fusion of these fermions. Yes?
So is a Cooper pair a triplet or a singlet? Because if you combine two fermions, two electrons, then you get either total spin 1, which is a triplet, or total spin 0, which is a singlet. So I'm performing.
Yes, that's a great question. I'm going to get to exactly that example in a little bit when I talk about some weird things that happen with anyon. In general, it can be both. It can be either spin 1 or spin 0. But they're both bosons, which makes fermions kind of boring. In that you always fuse them and you always get a boson. Not necessarily definitively spin 1 or spin 0, but a boson. And so the kind of what Kawagoe and Levin described in their paper is a method to compute kind of the statistics of particles within a lattice model. More generally, it's more general than lattice models, but they do it, part of their paper is applying this to lattice models, and specifically the toric code, which is why I've been talking about this weird example called the toric code for the past however long. So we first bring, okay, so we start with some fusion of anyons. Oh, sorry, spoiler alert. We start with this fusion of quasiparticles, and then we split them apart, and then we bring one around the other. And then the other one, we don't bring them around the other. So these two states should be entirely the same, except for these exchange statistics, which we can define as the phase difference between these two states. Right? Did everyone see that? We're just, in one case, we're exchanging the particles, and in the other case, we're not really exchanging the particles. Even though they end up in the same place, you wrap one around the other in one case, and you don't in the other. So let's use this formula, because this gives us like a mathematical formula we can just kind of plug and chug to compute the statistics of the quasiparticles in the toric code. Yes.
So on the previous slide, that's neither boson nor fermion species.
So this is the most general case. So these can be bosons, these can be fermions, these can be, well, we'll see what they can be. It can be just about anything.
Are the M's? What are the M's?
Oh, okay. Yeah, sorry, I didn't really define this. So the S is the splitting operator. So it's the operator that takes this fusion of quasiparticles and splits them apart into A and B. Yeah. And the M is movement. So it's these are operators that move the fermions like physically from one location to the other. So using these movement and splitting operators, once we can define these movement and splitting operators, we'll be able to compute these statistics. And so we'll start with the electric charges, because they're probably the easiest to actually see in the torque curve. We can move one electric charge to another location by applying sigma x operators. So we start with the vacuum, and so we have that the fusion of two electric charges is the vacuum. This is a kind of wrap your head around this, but you're able to split the vacuum into two of these electric charges, because we start with a completely fine, like ground state lattice, and we are able to create two of these electric charges. And then once we have these two electric charges, we can then apply the movement operators in all of these cases. And then we also split, and then we apply the movement operators. And this is kind of boring because the states are identical. So we get that this R symbol, which we define as this, the R stands for statistics for some reason. We get that this equals 1 in the case of two electric charges. And I'm just going to hand wave and say it's by duality. We get the same thing with the M charge. It's basically the same thing.
So these diagrams are supposed to sort of match the paths on the previous slide?
Yeah, so the idea is that these little green dots, I'm sorry they're not that visible, but the green dots are supposed to be these electric charges, these defects. So you'll see at each of the green dots we have this odd number spin up and spin down. And each place where there is a green dot we have an even number. So the red paths are the spins we have to flip in order to move, because each red is basically an application of sigma x. So we apply sigma x here, and then here, and then here, and then here, to get to our anyons from their initial state to their final state. But something weird happens if we try to do this with the fusion of E and M. Where here we're defining the fusion and just kind of putting the particles at, because they live in different worlds, we're going to put them as close as possible. So if you do the exact same procedure as we did on the previous slide, where you're kind of moving it down and then moving the other one over and doing all kinds of shuffling, because of the way the sigma matrices interact, we get a minus sign here. And so we get that the R symbol for the EM fusion, where we tie one of these electric charges to the magnetic charge, is -1. Even though I just said the fusion of two bosons is a boson. So what's happening here? We get that the fusion of these two particles where R equals 1 becomes a new particle where R equals -1. So what's going on here are anyons. So now I'm however long into this presentation, I'm finally going to define what an anyon is. An anyon is just a quasiparticle that's neither a boson or a fermion. And they're completely characterized by these anyon theories, where you have some set of anyon types, and you have a way of fusing these anyon types. A mysterious symbol I'll call F, which I haven't defined yet, and the R symbol we saw earlier, which is the statistics of these two particles. Yes?
So they're U1 because they're abelian?
Yes, so spoiler for the rest of the talk. The paper only discusses abelian anyons, but there are other kinds of anyons that we'll see later in the talk. This is straight out of the paper, by the way. So yes, the paper only touches abelian anyons. So what went wrong in order to have, like, why don't these anyons exist as real particles in 3+1 dimensional space? And that's just kind of because performing the exchange twice looks like you drag the particle around once and then around again. So it's just doing a loop around the other particle. So in 3 dimensions, you can pick this up out of the presentation and contract it to the identity. And so you know that applying this exchange twice must result in either +1 or -1. Applying this exchange twice must result in +1, which means applying it once must be + or -1. But in 2 dimensions, this is not a contractible loop. So there's no way to take this loop and turn it into the identity. So our exchange statistics can really be anything, and that's why these are called anyons. And so this is what I mean by the hole in the statistics theorem. It's right here. That's the hole. So now I can finally talk about the fusion of these anyons. And so I have a little quiz for you all. If you fuse the first two, and then fuse the third, is this going to be the same? Is this necessarily, and you get the same anyon either way. Is this going to be the same as if you fuse the last two first, and then the first? Who thinks, oh, they're obviously, they end in the same place, it's the same anyon, like obviously they're going to be the same. Okay, one hand up. So everyone else read the paper and realized, oh no, these are not necessarily the same state. They can differ by a phase factor, as a lot of things here. This is all very reliant on the fact that global phase doesn't really matter in quantum mechanics. So we just get these arbitrary kind of phase factors everywhere, and this is one of those places where they show up. So we define the symbol F that I mentioned was kind of mysterious earlier as the phase difference between these two fusion states. And so you'll notice I talked about braiding first. Most of the actual paper is talking about how to compute F for all these models, because it's one of the pieces you need to characterize anyons. Remember, I had this whole laundry list, and F is one of them. So now that we've shown that fusion can kind of be whatever, how wild can fusion get? Well, if you take in quantum mechanics 1, you learned this literally today, that if you have two spin 1/2 particles, they fuse into the direct sum of a spin 1 triplet and a spin 0 singlet. And so you get this idea that these can really truly fuse into different particles depending on the state of the system. We just don't really care about that as much because these are both bosons by the spin statistics theorem. And so what if quasiparticles could fuse into different anyons depending on their state? And so here's where I can define abelian and non-abelian anyons. Did anyone have any questions about that whole last section about statistics? No? Great. I can bring up that, oh yes.
So the fusion operator is what?
So the fusion, this is going to be a property, it's not really an operator, it's a function out of your set of 3 anyons into U1, F8. So you know that like F is determined entirely by these 3 anyons. Like there's always going to be a well-defined F for any triplet of anyons.
Wait, so then, because in your graph there's a fusion order, but when you do the F thing, you don't really get a fusion order. What?
What's
Like in your graphs, A and B fuse first.
Yes. This,
Yeah. But when you do F, A, B, and C, you really don't know which one's fused.
so this is not an operator, right? So this is the translation. So what we do is we pick a fusion order and say to translate from this one, from this state to this state, we need to apply F.
Oh.
So F is not the actual thing. It's not an operator that acts on your system. Like there's not like something you plug into the Torah code and say fuse all 3 of these at once. This is the way you translate between fusing 2 at a time. And depending on the way you fuse 2 at a time, you get different phases, and that's what this F accounts for. I will say, the name statistics, you might be wondering what does this have to do with statistics? It's mostly just historical baggage, because particles with different statistics, like real particles with different statistics, obey different statistical distributions. That's why they're called statistics. But here it's basically just historical baggage. So we define an anyon as abelian if it has exactly 1 fusion outcome. But we can also have anyons that are non-abelian, so they have multiple fusion outcomes. So Kawagoe and Levin, as I already mentioned, they only consider abelian anyons. But we can consider we can consider non-abelian anyons as well. But we better make sure that these are actually useful and not, because right, we're all physicists, we care about useful things. I'm going to take a little digression to talk about the kind of experimental history of anyons, or like how we know that any of this is actually relevant to reality. So anyons are first theorized in 1977 as just like, hey, there's this weird kind of exception in 2 dimensions where you have this kind of hole in the middle, this literal hole in the spin statistics theorem, where you allow these anyons to exist. This is a lot of people kind of converged on this idea at the same time, around the same time, within a few years of each other. In 1982, like how we get a kind of unexpected result where we observe the fractional quantum Hall effect for the first time. And this is where anyons really start to, this is where the name anyon is first coined in describing this effect. Because this is where we started lending credence to this idea of, oh, maybe these are actually useful to describe systems we do. Then 40 years go by. And we don't get real definitive, nobody doubts it evidence of anyons until 2020. Actually, two different groups. I wish I took notes so I could be like, oh, these are the groups. I don't know. But we get our first definitive detection of anyons in 2022. And then just a few years later, Google surprises a lot of people by finally detecting and braiding these non-abelian anyons that are more interesting. You might be wondering why is it so soon after these I thought abelian anyons were supposed to be easy and non-abelian anyons were supposed to be hard. Non-abelian anyons have a lot of signatures to look out for, which is what makes them not easy to detect, but easier to detect. So so I said they mentioned Ising anyons. That's a type of non-abelian anyon model. They're also not that good for topological quantum computation because they're very limited in the kind of computations they can actually do. So I'm going to pick a better anyon model to teach all of you. So these are Fibonacci anyons. There's only two anyons here. There's the vacuum and there's this tau particle. And so the fusion rule with tau is that you can take two taus and either fuse it into the vacuum or fuse it into another tau. So if you take 3 taus, if you just do this math out like it's basic algebra, then you get that there's 2 taus and a vacuum. And so this number 2 here is a signal that there are actually 2 pathways to go from 3 tau states to a single tau state. There's the one where you pass through a tau here and the one where you pass through a 1 here. And this is very interesting because these outcomes are mutually exclusive, which means in quantum mechanics, they're orthogonal. Like if you any measurement, it can only be one of these, right? And so these are orthogonal states. And therefore, we can use them as the basis for a qubit. Which is very, very weird. Because if you're Joe Biden over here, right? And you're looking at this is a superconducting qubit. At least you can look and be like, here's where the qubits are. They're the grounded excited states of this superconductor. Whereas, like in photonics, like you look at the state of the photon, and that's where your qubit is. But in topological quantum computing, where is your qubit? It's not really, there's no real point in the whatever topological quantum computing apparatus you could be in and be like, there's where the qubit is stored. It's stored in these kind of abstract fusion trees, which are just kind of representations of what you can do after you've already applied the quantum computation. And so I'd say just take a moment to convince yourself that these do work as genuine basic states. And if anyone has any questions on anything like this,
On slide 24, could you elaborate more on the notation used, the multiplication?
yes. So this is kind of the standard notation for describing fusion, but really you can think of these as analogous to a tensor product, and this is analogous to a direct sum. So what this top equation represents is just the possibility that 2 taus can fuse either into a vacuum, which is the 1 state, or a tau, which is a tau state. So then if you fuse another tau onto that, then you just kind of treat this multiplication normally, where it distributes over this direct sum. And so you multiply the 1 by tau, you get tau. You multiply the tau by tau, and you get 1 plus tau. And so together, that's 2 times tau plus 1.
So 2 times tau in this context is just a placeholder for either of the 2 pathways.
Yeah, so what the 2 represents is these 2 pathways that I've written out, where you have this you have 2 different ways you can reach tau from 3 taus.
Okay. So there's no notation to differentiate between these 2 different pathways.
This is just shorthand. Like these are very distinct outcomes. I mean, they're orthogonal states, but this representation is just telling you that there is this degeneracy. It's not really saying anything about the degeneracy.
Okay.
So you can imagine you fuse another tau onto that, so you're gonna get 3 tau plus 2, and then 5 tau plus 3, and then 8 tau plus 5. And that's why they call it Fibonacci anyons. They were not discovered by Fibonacci. I think he was a bit too early for that. Yes.
Just to make sure I understand this, on that left graph, where the first two fuse into a tau, there could be a third graph drawn where that middle tau, or like the halfway down tau, and the one that's up on the right, fuse into a 1.
Yes, exactly. That's what the 1 represents. That's just another fusion outcome.
So it's like 3 outcomes.
Yes, there are 3 outcomes. There are reasons we can't use the outcome that fuses into 1 for quantum computation. But we can use these now because there's no way to get it to talk to the fusion outcomes that fuse into tau. So we just get these 2 completely isolated systems. But these 2, as we'll see, these 2 can talk to each other. So these 2 can be.
Can you just draw that third fusion tree?
Yes. I don't know what class is here.
It does matter.
Very topical. So these tau fuse into tau, and these 2 taus fuse into 1. So that's the first thing. So now that we're working in this non-abelian world, we don't have FNR symbols that map nicely into E1. As you pointed out, like you get these matrices now, where now we're not just considering like one possible fusion outcome. We need to consider all possible fusion outcomes. And in general, this F symbol is allowed to mix fusion states. And in fact, I'm not just writing this down like willy-nilly and saying, oh, I should probably mix fusion states. These F and R symbols are fixed by certain consistency conditions. So we know that this F will mix fusion states, and R does actually result in different phases after fusion. So this is why it's kind of weird. You perform these braids and using the R operation, but you don't make the measurement until after you start fusing everything together. So in general, you get these unitary matrices. And the surprising result about these specific unitary matrices, and the reason why Fibonacci anyons over Ising anyons are interesting, is that these form a dense subset of SP2, which means we can get any quantum algorithm just by performing these 2 braids. You might be wondering, how can this be extended to multi-qubit systems? It can. You just braid more anyons. So in general, these are universal for quantum computation. And that should be really surprising, because we just have 2 matrices, right? You can see R to the 10th is the identity. And F inverse RF to the 10th is also the identity. But together, they form this dense subset of this space of all computations. Wild, isn't it? So in general, the recipe for topological quantum computation is that you initialize some number of anyons, you braid them to perform unitary operations on this basis of fusion outcome, and then you measure states by measuring the specific fusion channel that the anyons go through. And this satisfies basically everything we could possibly want from quantum computing. This braiding is topological, which means it's very robust against potential errors. The basis qubit states are they're very you're not going to get a lot of decoherence out of these basis qubit states because they're fundamentally different. And you also don't get, like, if you have a quantum system where your qubits are stored in a ground versus excited state, you're going to get a lot of push from that excited state to decay. But that doesn't happen here because these are all separate ground states. So your basis qubit states are very well protected. And so we end up getting these incredibly error-resistant qubits and gates. In practice, I don't know if this will ever be realized experimentally. I hope so. But funny story, I ended up on a call. If any of you know who Travis Scholten is, he's kind of the business head of IBM's quantum computing, I guess, division. And he told me that topological quantum computing was 22nd century technology. So maybe in 100 years this will be realized experimentally. But there are teams working on it now. Microsoft, Continuum, Google, yes.
What entry you said?
20 seconds, yeah. So 100 years from now, maybe we'll get topological quantum computing.
Okay. Longer than the time your acid was
We're gonna do a Brian Johnson and like try to be alive for that long.
Yeah.
Yeah. Trust me, the future's gonna be great. Once we get this going. Any questions about anything? Yes.
What kind of Hamiltonian do you have to engineer to get these like tower type visions?
Very weird ones. So we've seen the. I don't know if I can answer that. I know fractional quantum Hall states. Instead of we never observed tau. We've observed obviously using anyons. We've never had direct confirmation of Fibonacci anyons. They've been used to describe certain fractional quantum Hall states with certain Hamiltonians. So that I can say there are Hamiltonians that do describe Fibonacci anyons. What they look like is very weird. A lot of long-range entanglement nonsense.
So you need long range interaction.
Yeah, so very typically with these non-abelian anyons, you'll need long-range entanglement. Because, yeah, that's how you get all these great properties. Yeah.
So in slide 25, I believe there's a mention of, I think it's slide before that. Oh, I think it's slide 26. There was like a mention of like an experimental observation.
Oh, yes.
Yeah, this one. Yeah. Could you elaborate more on the details of it?
So I'm not an experimentalist, but I can say, yeah, like braiding, because the braiding of non-abelian anyons results in different phases for these different subspaces, you can use it to kind of pick out, like certain, if you have these non-abelian anyons, you can show that they exist by picking out certain subspaces of your original space. And so Google got there first with these non-abelian anyons. Quantinium comes a bit later, 2023. If you're talking about abelian anyons, I can tell you definitively one of the experiments is really cool. They made this like tiny little particle collider in this, like a miniature little particle collider in this condensed matter system, where they're able to do kind of particle collider experiments and actually like find like evidence for these anyons, like as you would find evidence for particles in particle physics.
What is the Hamiltonian of the Ising anyons?
I have no idea why they're called Ising anyons. So these are, because Ising obviously didn't come with this easier either. He was also a bit too early. In general, what people look at Ising anyons through the lens of Majorana zero modes, which are, there's very specific, like if you have, the toy model I know, is that you get certain Hamiltonians with a bunch of fermions. And what can happen sometimes is these fermions like split down the middle. So you sometimes get these, this like trivial state where you have a bunch of fermions all in a line, and that's kind of boring. Or you can get these, you like split apart and then refuse these middle parts. So you have these fermions in the middle, but at the end you have these free Majorana zero modes, and these are Ising anyons that you can use that. And as is kind of like non-trivial, you can use these for quantum computation, all these little weird end states. I can't write any of these Hamiltonians down for me, but this kind of setup does exist. This spin chain. What they call it.
So they're topologically protected.
Yes. Everything here is topologically protected. Yes.
It's a weird one. A few years ago, I read about Microsoft at like UCSB. They were doing something like this, and I saw like Majorana in there. And my very limited knowledge tells me that Majoranas were like something's its own antiparticle or something.
Yeah. So the fusion rule
What is
for
that? Yeah.
Ising anyons, I can talk a little bit about them. They're a little bit more complicated. So you have three particles. One, I think he's sigma, and psi, where psi is a standard fermion, and so sigma fused with sigma can be one or it can be psi. So these can fuse to themselves, or they can fuse to a fermion. So this is how you get this non-abelian stuff. And then when you go and compute the F and R matrices, they don't quite work out to get you universal quantum computation. But they're still interesting to some people.
This is somewhat of a general question. So we have abelian anyons, non-abelian anyons. So, or is the fusing operator like closed within these two categories? So would fusing two abelian anyons always give you an abelian anyon, vice versa?
No. So, okay. So in this Ising model, Ising anyon model, we have this, the fusion of two of these sigmas fusing into one 4 psi. Both of these 1 psi are just kind of standard particles on their own. Like obviously vacuum fuses into vacuum. And psi also fuses to itself. So this is, you can have abelian and non-abelian anyon models. Which a non-abelian anyon model, I think they're generally considered as non-abelian if you have like one of these weird kind of multi-fusion states. Abelian anyons are one where all of the anyons in the system always fuse to one determined fusion outcome. So yeah, you're not going to get multiple fusion outcomes out of every anyon.
So biabelian isn't commutative with respect to fusion or braiding?
I can talk a bit about the name abelian. So abelian comes from the fact that all of these F symbols are just phases. So U1 is an abelian group because you multiply two phases, it's just multiplication. Whereas in the non-abelian case, we get matrices. And matrices are in general non-abelian. So that's why they're called abelian versus non-abelian anyons. It's because these matrices are either 1 by 1, so they're abelian, or they're n by n, so they're not abelian.
Talk a bit more about like the concept of braiding, like in terms of like realizing it experimentally.
So I'm not an experimentalist. So braiding is what we like to call an engineering problem. But in general, it literally does. You literally are physically moving these anyons around each other. You have some kind of potential they're trapped in. And you are literally braiding. Let's see if I can draw this right. So you get your potential well with your anyons, and you literally move them around each other.
So when you have that graph where it's like the vertices and their duals, both sides were showing like what braiding does, right?
Let me see if I can put that.
So that's
This
like
one?
a demo of braiding.
Yeah. So this is exactly, well, this isn't quite like braid because we're not fully exchanging any of the particles here. This is how we measure R. So this is the statistic you get if you braided them. But we don't never actually make the particles go in the loop. We could, but in this case we don't really need to compute R.
So it's, never mind.
So how would you compare F in this sort of code for
Um,
EM fusion?
Yes, so this was in the paper.
It's also a homework problem for Michael Levin's class.
Oh, is it actually?
Yeah.
Oh, well, I'm not going to do your homework for this. It's in the paper though.
Yeah.
I mean,
So I use electric fields to physically
Oh,
move two electrons around each other. That would be considered fermion.
Right, because they're that.
Wait, what's up?
You heard that braiding is actually physically moving the particles around
Yeah,
each
But
other.
it's just mutually.
So if I were to use an electric field to rotate two electrons around each other, that would also be considered braiding.
Yeah, depending on, because braiding has to be an adiabatic process. So you have to make sure you give it all really carefully. In principle, that is basically how you do it though. Or magnetic fields. So one of the two is how you actually like move the atoms around.
I think, any more questions? Or we can wrap up and people can continue to talk to Ryan after.
Any other questions?
Not?